The following video is on differentials. Consider the following function f of x and the point x, f of x on the function. If we look at a point that is relatively close to this first point, let's say that the x value of it is x plus delta x, where delta x is a little bit, it shifts it just a little bit to the right. And then we plug in this value, x plus delta x, into our function f, so we get the new y value. So that means that the distance between the two x values is called delta x. We will similarly call the distance between the two y values delta y. Now we'd like a way of approximating delta y. So one way that we can do that is to look at the tangent line that passes through the point x, f of x to the curve f. If we look at the y value on the tangent line just above x plus delta x, then we call the distance between the two y values, the one on the tangent line and the original point, we call that change in y dy. Similarly, we can call the change in the x values dx. Remember that the slope of the tangent line is f prime of x, and we know that if delta x goes to 0, then dy is going to be getting closer and closer to delta y. Recall that dy by dx equals f prime of x. This is just two different ways of writing our notation for the derivative. If we multiply both sides by dx, however, we get that dy is given by f prime of x times dx. dy is called the differential of f evaluated at x. Delta y is sometimes difficult to compute without a calculator, but dy is usually very easy to compute. In this video, we'll look at some examples and we'll see how differentials can help us to calculate or compute things, especially things like propagated error. Let's start with the following example. F of x is going to be the square root of x is 4, and delta x is 0.1. We want to find delta y and dy. Remember that delta y is actually the difference between f of x plus delta x and f of x. So if we evaluate f of x plus delta x, that'll be f of 4.1. And if we evaluate f of x, that'll be f of 4. By using my calculator, I found that f of 4.1 was 2.0248, and f of 4, we all know the square root of 4 is 2. So the difference between these two values is 0.0248. So this is the value of delta y. dy, on the other hand, is found by taking f prime of x times dx, just like we saw in the previous slide. So the first thing I have to do is find f prime of x. We know from experience that f prime of x is 1/2 x to the negative 1/2. And remember that delta x is the same thing as dx. So 1/2 x to the negative 1/2 times delta x is the same thing as 1/2 times 4 to the negative 1/2 times 0.1. This is the same thing as 1/2 times, and then 4 to the negative 1/2 is the same as 1/2, times 0.1 is the same thing as 1/10. So we're going to have 1/4 times 1/10, which ends up being 1/40. If we look at the decimal value for 1/40, we see that it's 0.025. So notice that these two values, delta y and dy, are actually very close to each other. Unfortunately, to calculate delta y, we needed a calculator, but to calculate dy, we didn't need anything fancy. Differentials can be used to estimate error in scientific work. So for example, if we measure x and we know that there's a possible error of some amount delta x, and then we use the measurement that we took to compute other things such as volumes or areas, the error will distribute throughout our computation. This error is given by delta y. So delta y, remember, is the exact error that we should have. This is called the propagated error. Since dy approaches delta y as delta x gets closer and closer to 0, we can use dy to estimate the propagated error. So the relative error is given by delta y over y, or in other words, the actual error divided by the actual y value. So this is sort of like a percentage. So suppose a scientist is measuring the radius of a tube and the measurement comes out to be 6 centimeters. However, she knows that her tools don't measure precisely. If she did measure precisely, she would have found the radius was going to be exactly 6.15 centimeters. So, r equals 6 centimeters and delta r equals 0.15 centimeters. The area of the circular opening is given by pi r squared, and so we can easily compute the area when the radius is 6. Notice that 36 pi times centimeters squared is the same thing as approximately 113.097 because we're taking pi to be approximately 3.14159. We can also compute the area if the radius is 6.15, and we end up with 118.823 centimeters squared. So the propagated error, which remember is the exact difference of these two values, is given by approximately 5.726 square centimeters. We can estimate the propagated error using d, in this case dA. dA by dr is the derivative of the area formula, which is given by 2 pi r. So if we move the dr to the other side, we get that dA is approximately 2 pi r times dr. Plugging in 6 for r and 0.15 for dr, we end up with 5.655 square centimeters, which notice is very close to the propagated error, which we found was 5.726 square centimeters. Notice that the nice thing about this was that we didn't need to do any advanced computations or estimate, what 6.15 squared is. We were able to do this pretty easily. The relative error, remember, is sort of like the percentage. It's the delta A divided by A. And if we wanted to approximate it, we could do dA divided by A. And in looking at the formula, dA, remember, was 2 pi r times dr, and A was pi r squared. So the pi and one of the r's cancel from the top and the bottom, and we're left with 2 dr over r. If we plug in for dr and r, we end up with 0.05. So the relative error is about 5%. Let's look at another example. So suppose a scientist measures the radius of a tube to be 6 centimeters. He's unsure how carefully he measured, but he wants to be sure that he has a percent error in the area of the circle of less than 3%. So dA by A, in other words the relative error, he wants to be 2 pi r dr, which remember is the dA value that we found on the previous slide, and A is pi r squared. We can cancel out the pi and one of the r's from the top and the bottom, and we're left with 2 dr over r. This is the relative error, or the percent error. We want this to be less than 0.03. Now all we have to do is figure out what dr must be in order to keep that. So we can divide both sides by 2, multiply both sides by r, and we see that r must be measured within 1.5% accuracy. So we move the decimal point over 2 places to get the percentage. We can also do linear approximations using differentials. Differentials can be used to estimate quantities. So, for example, if f of x plus delta x is hard to compute, remember that delta y is given by f of x plus delta x minus f of x, but this is approximately dy. So we can rewrite f of x plus delta x as approximately dy plus f of x. I just moved the f of x to the other side of the equation. Remember that dy is given by f prime of x times dx, so therefore f of x plus delta x can be approximated by f prime of x dx plus f of x. Let's look at an example. So let's estimate the square root of 4.1 using differentials. We're going to let our function f of x be the square root of x, and x will be 4. Notice that we know how to evaluate f of 4. Notice that the difference between the value that we want to take the square root of and the value of the square root of x, the input in these cases is differing by 0.1 or 1/10. So I'm going to let delta x be 0.1. So now we look at f prime of x. We end up with f prime of 4 being 1/2 times, and then 4 to the negative 1/2 is just 1/2. So we end up with 1/4. So f of 4.1, using the formula from above, is going to be dy, so that's 1 over 4 times 1/10, plus f of x, which we know f of x, or f of 4 in this case, is 2. So I'm going to have 1/4 times 1/10 plus 2 is 1 over 40 plus 2, which is 2.025. If we wanted to see the actual value, plugging it into my calculator, I got 2.0248, which notice is very close to the approximated value that we just did without a calculator. Let's try to estimate sine of 0.1 using differentials. Let f of x be sine x. X is going to be 0. Notice that we know how to compute f of 0 without a calculator. The difference between our input 0 and the actual value that we want to input is 0.1. So delta x is going to be 0.1. Now we want to compute f prime of x, which we know is cosine x. So f prime of 0, or cosine of 0, is 1. We now can find that dy is going to be cosine of, in this case, 0 times delta x. So we're going to have cosine of 0 times 1/10 plus, now we want to do the actual value of sine of 0. So we end up with 1 times 1/10 plus 0, or 1 over 10. The actual value of sine of 0.1 is 0.099833, so we ended up being actually very close.